learners chemistry, and welcome to the mixed practice number 2. What we're going to do is I'm just going to talk through the working of these problems so that way you can hear it and think about it, and hopefully it will help you as you study for the quiz or test or exam or whatever. All right, here we go. Number 1, the formation of calcium chloride. So we would think to ourselves, calcium chloride's ionic, made of 2 elements. Synthesis, taking 2 elements, is the simplest way to make it, right? Take some elemental calcium, elemental chlorine, and make some calcium chloride. Alternatively, we could make it using one of our other types of reactions, right? We could do a element plus compound, where we could take calcium as our element and any other metal chloride as our compound, and then produce calcium chloride and some other metal. That is also a quick and simple way to do it, right? As a third alternative, since calcium chloride is an ionic compound, we could also do a double displacement, right? Whereby double displacement, I just mean any of the types of reactions where we take 2 ionic compounds and switch the cations. So that means calcium would be the cation in one compound, chlorine would be the anion in the other compound. So when the cations switch, we would end up with calcium chloride as one of my products. Any of these 3 methods would be fine for producing calcium chloride. All right, next one, oxygen is produced. So here, oxygen is an element, so we have to be a little bit more thoughtful about how we do it, right? And so the simplest way to produce an element would be through the breaking down of a binary compound. So anything that contains oxygen, I've gone with magnesium oxide, but it could be any metal oxide, non-metal oxide, doesn't matter. If we decompose it, we're going to form oxygen as one of our elements. All right, next up, we've got aluminum is exposed to oxygen. So if we think about this, right, we've got 2 elements. All 2 elements can do is form a compound. The compound's formula is governed by Chapter 5 rules, obviously, and then we balance. It's solid because it's ionic and there's no water present. Number 4, solid sodium bicarbonate is added to aqueous sulfuric acid. Solid sodium bicarbonate, aqueous sulfuric acid, and then we would just look at this and be like, ooh, 2 ionics or essentially ionics. Let's switch the cations. And we think to ourselves, there's water present. Sodium is soluble, so that's going to be aqueous. And then water and CO2 is what happens from that H2CO3 intermediate. All right, now we've got number 5, where we have aqueous solutions with lithium hydroxide. So we need a formula for that, and iron 3 chloride, formula for that. And then we'd look, switch the cations. So we would switch the cations, balance their charges to write new formulas. Iron 3 hydroxide is a solid because hydroxides tend to be insoluble, with exceptions being the always soluble ones, right? Lithium chloride is definitely soluble. There's water present, so it's aqueous, right? Now, in order to get to the net ionic, because it says to provide one, what we're going to do is we're going to take everything that is both aqueous and ionic, it must meet both criteria, and dissociate it into its respective ions. Dissociate meaning break it apart into its respective ions, which goes back to those pictures from the beginning of Chapter 7, where it shows that ionic compounds that are dissolved in water will break apart into its ions, right? Which, going back to the last unit, when we did our lab, that's why ionic compounds in water tend to conduct electricity, because once they're dissolved and we have the free-floating ions, right, those free-flowing charged particles can conduct electricity. So anyway, we dissociate everything that is both aqueous and ionic, bearing in mind the respective numbers of each. Then we cross off the spectator ions, and then whatever is left becomes our net ionic. And that is the final answer. So note that here it just asks to provide a net ionic. So if you don't need that step in red, you don't have to do it, but it can be helpful. Number 6 says we have some aqueous hydrochloric acid and potassium hydroxide are mixed. So first we need formulas for hydrochloric acid and potassium hydroxide aqueous. All the charges are 1, so the writing is very simple. And we would switch the cations because we have 2 of what are essentially ionic compounds. And we have KCl, aqueous, because group 1, H2O, which is a liquid because it is a molecular compound. So it's a liquid and it's water. So again, it must be aqueous and ionic to dissociate into its respective ions. So HCl, we'll write it dissociated. KOH, write it dissociated. KCl, also write it dissociated. H2O is not ionic, nor is it aqueous, which means that when we get to that water is going to get written as H2O liquid, which means that we do indeed have a net ionic when we are done, right? So this is a good example of a type of reaction where there is definitely a chemical change occurring, right? The components of whatever's in our test tube or beaker are not the same as they were before, even though we can't necessarily see that. All right, next page. Next up, we've got number 7. Liquid hexane is combusted. So that's your clue that whatever it is being reacted with oxygen. And in this case, since it's a CH compound, it produces CO2 and H2O. H2O in gas form because combustions produce a lot of heat. Then the only trick is in balancing, where we would put a 6 and a 7 to balance the carbons and the hydrogens and realize, odds and evens. And so then we would put a 2 in front of the C6H14 because that's what's giving us the odd number of oxygens. And so then we would redo the carbons and redo the hydrogens and then go back and do that oxygen one more time. And so when we add them all up and then we divide by 2, we come up with 19. All right, next up, magnesium is added to tin for chloride. So we would take our magnesium, solid, aqueous tin for chloride, and then we would look at these and say, ooh, element plus compound. The element will switch with whatever it's most similar to, which between tin and chlorine is the tin, right? And then we'll produce a new element and a new compound. Next up, sodium chloride is decomposed, meaning sodium chloride is the only reactant, and it's binary, so it'll decompose to form the respective reactants it is made of, right? Bearing in mind, like chlorine is diatomic, but sodium is not. Number 10 says we have aqueous solutions of ammonium chloride and potassium hydroxide are mixed. So we would write down our formulas and our states. We would look at them, 2 ionics, we would switch the cations, and in doing so, we would realize, oh, look, this is one of those times we form an intermediate. This time it's that ammonium hydroxide intermediate, so we would erase that and then write down instead the NH3 and H2O that ammonium hydroxide would break down to form, which is why we get what we get. All right, next up, aqueous solutions of lead to acetate and nickel to iodide are mixed. So first we got to get formulas and states for each of these. And then we would look at what we have and say, oh, look, it's more ionic compounds. Let's switch the cations. And in doing so, we get our nickel acetate and we get our lead iodide. Acetate compounds are always soluble. Iodine is one of those exceptions where it's often soluble, with a few exceptions, lead being one of them. So make sure you know those few exceptions, which is why we know it should be a solid for its state. Next up, we have lithium carbonate, solid, is added to aqueous phosphoric acid. So we have a carbonate plus an acid. First, we'd switch the cations, right, and we'd get our lithium phosphate. Lithium is group 1, so it's definitely soluble. And then we would come up with our H2O and CO2 again as the result of carbonic acid breaking down. And then the only trick would be to make sure we balance it correctly. Fixing the odds and evens problem first is easiest in terms of how to balance that. All right, zinc is added to aqueous chloric acid, not to be confused with hydrochloric acid. So we would take our chloric acid and our zinc and we'd say, oh, let's switch. We have an element plus a compound. So the element switches with what it's most similar to. In terms of hydrogen and the chlorate, zinc is more similar to the hydrogen. They both play the role of cations in compounds. All right, chlorine gas is bubbled through aqueous calcium bromide. So, remember, bubble just means passed through, right? So they're just being allowed to interact, which means they can react. Element plus compound. The element, chlorine, will switch with whatever it's most similar to, and in this case, it is most similar to bromine. So then the chlorine and the bromine will switch, producing a new element and a new compound. Now, do bear in mind that if you were tempted to combine the chlorine and the bromine, that should strike you as weird because you don't know how to write that formula, because you don't have any rules to govern how many chlorines and bromines there are, because they're both anions, right? So, we should use our common sense there, and our rules should help to guide us. All right, next up we have isopropanol is exposed to a flame. So exposed to a flame is your key for combustion, which means really it's just a CHO compound plus oxygen produces gaseous CO2 and gaseous water, and then the only hard part is to balance afterwards. Like we said before in class, sometimes it can help to condense the hydrogens in a CHO compound just because it's easier to look at, and it's we are more likely to get the math right in terms of counting out that number of hydrogens, right? So in this case, we would do the carbons and then the hydrogens and realize that the oxygens don't work. So we would erase those and then put a 2 in front of the CHO compound and try again, right? So we'd rebalance the carbons, rebalance the hydrogens, sum up the oxygens, and then remember that there are 2 oxygens in that CHO compound and factor that into the number we put in front of the elemental oxygen. Finally, we have rubidium is exposed to fluorine element and another element. What? We're going to combine them and form a new compound. Ionic compound, no water, so solid, and then we balance. All right, so for studying, you should be working on 1, knowing the types of reactions. I highly recommend that you make your own, just like we talked about for naming, right? Make your own chart, diagram, outline, flow chart, whatever, however you want to organize your thoughts, but create something on 1 sheet of paper that summarizes what to look for on the reactant side, what to do with those reactants, and how to get to the product side. You also need to make sure you know the states, which we talked about at the beginning of Chapter 7, how to assign them, and which ones you're responsible for knowing. A review of Chapter 5 would be helpful for most people, right? Just to refresh your memory on how to properly write formulas. And study and practice. There are blank copies on Schoology that you can use as needed. All right. Thank you for listening. Be good, and I will see you soon. Bye.